Tonight, we're going to explore one of the most fundamental properties of our universe: temperature. Not just the comfortable range we experience on Earth, but the absolute extremes. From temperatures so cold that atoms barely move, to conditions so hot that the very fabric of space and time begins to break down. By the end of this journey, you'll understand the full spectrum of heat and cold that exists in our cosmos, from near absolute zero to beyond the limits of conventional physics. Before we start, if you enjoy these deep explorations into the mysteries of science and space, a quick like or subscribe would really help the channel grow. Now let's begin our journey through the temperature extremes of the universe. Temperature is something we experience every moment of our lives. We feel warmth from the sun on our skin. We shiver in winter cold. We adjust our thermostats to maintain comfort. But temperature is far more than just a sensation. At its most fundamental level, temperature is a measure of motion. Specifically, it's a measure of the average kinetic energy of the particles that make up matter. When particles move quickly, vibrating, and bouncing around with tremendous energy, we perceive that as heat. When they move slowly, barely drifting through space, we perceive that as cold. Every atom, every molecule in the universe is in constant motion. Even in a solid piece of metal, the atoms vibrate in place. In a gas, molecules zip around at hundreds of meters per second, colliding with each other billions of times every second. This motion is what we measure when we measure temperature. The temperature scale we use most commonly is Celsius, where water freezes at 0 degrees and boils at 100 degrees. In the United States, Fahrenheit is more common, with water freezing at 32 degrees and boiling at 212 degrees. But for scientific purposes, particularly when dealing with extreme temperatures, we use the Kelvin scale. The Kelvin scale starts at absolute zero, the coldest possible temperature, where all thermal motion ceases. On this scale, 0 Kelvin corresponds to negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit. The advantage of the Kelvin scale is that it's absolute. There are no negative numbers. 0 means zero thermal energy, at least in classical physics. Room temperature, comfortable for humans, sits around 293 Kelvin, or about 20 degrees Celsius. The universe contains temperatures far beyond anything we experience in daily life. The coldest natural place we know of reaches temperatures barely above absolute zero. The hottest conditions approach temperatures so extreme that our current understanding of physics begins to fail. Between these extremes lies an enormous range, spanning more than 32 orders of magnitude. That's a 1 followed by 32 zeros. To put that in perspective, the entire observable universe is only about 93 billion light years across. If we represented the temperature range of the universe on a number line, where absolute zero was at one end and the Planck temperature was at the other, the temperature of the Earth's surface would be indistinguishably close to absolute zero. We exist in an incredibly narrow, incredibly cold sliver of the total temperature spectrum that physics allows. Understanding temperature extremes helps us understand the universe itself. Temperature determines the state of matter. At different temperatures, the same substance can be a solid, a liquid, a gas, or even more exotic states, like plasma or Bose-Einstein condensates. Temperature drives the fusion reactions in stars, creating all the heavy elements in the universe. Temperature shaped the early universe, determining how particles formed and how structures emerged. Temperature will determine the ultimate fate of the cosmos as the universe continues to expand and cool toward a final state of maximum entropy. Let's begin our exploration at the coldest end of the spectrum, at temperatures approaching absolute zero. The concept of absolute zero emerged from the study of gases in the 18th and 19th centuries. Scientists noticed that gases contract when cooled. In 1787, French physicist Jacques Charles observed that for every degree Celsius a gas cooled, its volume decreased by a predictable fraction. If you extended this pattern, the gas would reach zero volume at about negative 273 degrees Celsius. Of course, real gases liquefy before reaching this temperature, so the experiment couldn't actually be performed all the way to zero. But the mathematical extrapolation pointed to a fundamental limit. This temperature, where gas volume would theoretically become zero, was absolute zero. Later understanding revealed that absolute zero represents something even more fundamental. It's the point where all thermal motion stops, where particles possess only their minimum quantum mechanical energy, called zero-point energy. The third law of thermodynamics, formulated in the early 20th century, states that it's impossible to reach absolute zero in a finite number of steps. No matter how good your cooling technique, you can only approach absolute zero asymptotically, getting closer and closer but never quite reaching it. This isn't just a practical limitation of our technology, it's a fundamental law of nature. Why can't we reach absolute zero? The explanation lies in quantum mechanics and the Heisenberg uncertainty principle. If we could cool a particle to exactly absolute zero, we would know both its position, it would be stationary, and its momentum, which would be exactly zero, with perfect precision. But the uncertainty principle forbids this. There must always be some uncertainty, some residual motion. Particles at absolute zero would still possess zero-point energy, the minimum energy allowed by quantum mechanics. Despite the impossibility of reaching absolute zero, scientists have achieved temperatures astonishingly close to it. The coldest temperatures ever recorded, both natural and artificial, exist in a realm where the rules of classical physics give way entirely to quantum behavior. At these temperatures, matter behaves in ways that seem impossible, forming exotic states that don't exist anywhere else in the universe under normal conditions. These ultra-cold systems have allowed physicists to test fundamental theories, to observe quantum effects on macroscopic scales, and to develop new technologies that exploit the strange properties of matter near absolute zero. Before we discuss the coldest place humans have created, let's explore the coldest natural place in the known universe. About 5,000 light-years from Earth, in the constellation Centaurus, lies a nebula with an unusual shape. When first observed in 1980 by astronomers Keith Taylor and Mike Scarrett using the Anglo-Australian telescope, they noticed an asymmetry in its structure that vaguely resembled a boomerang. This gave the nebula its name, the Boomerang Nebula. Later observations with the Hubble Space Telescope revealed a more bow tie or hourglass shape, but the name had already stuck. What makes the Boomerang Nebula remarkable isn't its shape, it's its temperature. In 1995, astronomers Raghvendra Sahai and Lars Åke Nyman used the 15-meter Swedish ESO submillimeter telescope in Chile to measure the temperature of the gas in the Boomerang Nebula. What they found was astonishing. The temperature was approximately 1 Kelvin, or more precisely, measurements suggest the coldest regions reach about negative 272 degrees Celsius, negative 458 degrees Fahrenheit. This is just 1 degree above absolute zero. This is colder than the cosmic microwave. Background radiation, the remnant glow from the Big Bang that fills all of space. The cosmic microwave background has a temperature of about 2.7 Kelvin. The Boomerang Nebula is the only known natural object in the universe that's colder than the background temperature of space itself. How is this possible? How can something be colder than the ambient temperature of the universe? The answer lies in the nebula's extraordinary expansion. The Boomerang Nebula is a planetary nebula, though the name is misleading. Planetary nebulae have nothing to do with planets. They're shells of gas ejected by dying stars. At the center of the Boomerang Nebula sits a red giant star that's in its death throes. This star, once similar to our Sun, has exhausted the hydrogen fuel in its core and has swollen enormously. Now it's shedding its outer layers into space, but the Boomerang Nebula isn't a typical planetary nebula. The gas is being ejected at extraordinary speeds, about 164 kilometers per second. That's about 500,000 kilometers per hour, or roughly 310,000 miles per hour. For comparison, an F-16 fighter jet travels at around 2,400 kilometers per hour. The gas from the Boomerang Nebula is expanding more than 200 times faster. This rapid expansion is the key to the extreme cold. As the gas expands, it cools through a process called adiabatic expansion. You've experienced a version of this process if you've ever used an aerosol spray can. The compressed gas inside the can is under high pressure. When you press the nozzle, the gas expands rapidly as it escapes. This expansion requires energy, which comes from the thermal energy of the gas itself. The result is that the gas cools down dramatically. If you've ever noticed that a spray can get cold when you use it for an extended period, that's adiabatic cooling at work. The same principle operates in the Boomerang Nebula, but on a vastly larger and more extreme scale. The gas is expanding so fast that it's cooling faster than it can absorb heat from its surroundings. Even though the cosmic microwave background bathes everything in space with radiation at 2.7 Kelvin, the Boomerang Nebula's gas is expanding too quickly to equilibrate with this temperature. In fact, detailed measurements show that parts of the nebula are even colder than 1 Kelvin. Some regions may reach temperatures as low as 0.5 Kelvin, or about negative 272.65 degrees Celsius. That's just half a degree above absolute zero. These are the coldest temperatures known to occur naturally anywhere in the universe. Why is the gas expanding so fast? Based on observations and modeling, astronomers believe the central star is likely a binary system. The evidence suggests a smaller companion star plunged into the larger red giant millions of years ago, spiraling inward through the giant's outer envelope. This process, called common envelope evolution, would have released tremendous gravitational energy. The energy expelled material from the system at these extraordinary velocities. The resulting outflow contains about 1,000th of a solar mass of material per year. That's 10 to 100 times more than typical planetary nebulae. This massive rapid outflow is what creates the Boomerang Nebula's extreme cold. The Boomerang Nebula won't remain the coldest place in the universe forever. As the ejected gas continues to expand and disperse, it will gradually warm up as it interacts with the surrounding interstellar medium and absorbs radiation from nearby stars and the cosmic microwave background. Eventually, in perhaps a few thousand years, the nebula will fade from view, and its temperature will rise to match the background temperature of space. The central star will become a white dwarf, a dense stellar remnant about the size of Earth, but with a mass similar to the Sun. But for now, for this brief cosmic moment, the Boomerang Nebula holds the record as the coldest known natural place in the entire universe. While the Boomerang Nebula represents the coldest naturally occurring temperatures, human ingenuity has pushed even colder. In laboratories on Earth, physicists have created conditions far colder than anything found in nature, achieving temperatures that are mere fractions of a billionth of a degree above absolute zero. These achievements required developing entirely new cooling techniques, methods that manipulate individual atoms using lasers and magnetic fields with incredible precision. The quest to reach these ultra-low temperatures has been one of the great achievements of modern physics, opening up entirely new areas of research and leading to multiple Nobel Prizes. The journey to ultra-cold temperatures began with traditional refrigeration techniques. Conventional refrigerators work by compressing and expanding gases. When you compress a gas, it heats up. When you let it expand, it cools down. By cycling through compression and expansion, you can pump heat from a cold region to a hot region, keeping the cold region cool. This principle allowed scientists to liquefy gases. Oxygen liquefies at 90 Kelvin, nitrogen at 77 Kelvin. These cryogenic liquids became invaluable tools for cooling experiments. But to go colder, to approach absolute zero, entirely new techniques were needed. The breakthrough came with laser cooling, developed in the 1980s and 1990s. The basic idea seems counterintuitive. How can you cool something with lasers, which we normally think of as heating things up? The key is that lasers are perfectly tuned to specific frequencies. When an atom moves, it experiences the Doppler effect, just like a siren sounds different when an ambulance is moving toward you versus away from you. If you tune a laser frequency to be slightly below the frequency an atom would naturally absorb, the laser will only interact with atoms moving toward the laser source. When an atom absorbs a photon from the laser, it slows down. The atom then re-emits the photon in a random direction, but on average, the momentum transfer from absorption and emission results in the atom slowing down. By surrounding atoms with laser beams from all directions, each tuned to slow atoms moving in that direction, you create what's called optical molasses. Atoms become trapped in the intersection of these laser beams, slowed to speeds corresponding to temperatures of just a few millionths of a degree above absolute zero, a few microkelvin. But laser cooling has limits. At some point, the random recoil from absorbing and emitting photons starts to dominate, and you can't cool the atoms any further. To go even colder, physicists developed evaporative cooling, a technique inspired by how a cup of hot coffee cools down. When you have hot coffee, the most energetic molecules at the surface occasionally have enough energy to escape into the air. This carries away energy from the coffee, leaving behind the slower, cooler molecules. The average temperature of the remaining coffee decreases. Evaporative cooling of atoms works similarly. You start with a cloud of laser-cooled atoms trapped in a magnetic field. The magnetic field is shaped like a bowl, trapping the atoms. You then gradually lower the walls of this bowl, allowing the most energetic atoms to escape. The remaining atoms are colder on average. You repeat this process, gradually cooling the atoms to lower and lower temperatures. Using these techniques, physicists in the 1990s achieved a historic milestone. In 1995, two teams, one at the University of Colorado Boulder, led by Eric Cornell and Carl Wieman, and one at MIT led by Wolfgang Ketterl, cooled atomic gases below 1 microkelvin. At these temperatures, something extraordinary happened. The atoms underwent a phase transition into a completely new state of matter, called a Bose-Einstein condensate, or BOEC. This state had been predicted theoretically by Satyendra Nath, Bose, and Albert Einstein in the 1920s, but it took 70 years to achieve it experimentally. The achievement was recognized with the Nobel Prize in Physics in 2001. What is a Bose-Einstein condensate? At normal temperatures, atoms in a gas behave like individual particles, each moving independently. But as you cool the gas, the quantum mechanical wave function of each atom begins to spread out. At sufficiently low temperatures, these wave functions overlap. The atoms lose their individual identities and merge into a single quantum state. They become, in effect, one giant superatom. All the atoms behave in perfect synchrony, marching in lockstep according to the rules of quantum mechanics. This allows quantum mechanical effects, normally visible only at atomic scales, to become observable on macroscopic scales. You can see quantum behavior with your own eyes, or at least with sensitive cameras. Since that first achievement, many groups worldwide have created Bose-Einstein condensates routinely. The lowest temperature reported before 2003 was 3 nanokelvin, 3 billionths of a degree above absolute zero. Then, in September 2003, a team at MIT, led by Wolfgang Ketterl and David Pritchard, set a new record. They cooled a sodium gas to 500 picokelvin. That's 500 trillionths of a degree above absolute zero. To put this in perspective, this is more than 10 million times colder than the Boomerang Nebula, the coldest natural place in the universe. How did they achieve such extreme cold? The MIT team used a sophisticated combination of laser cooling, magnetic trapping, and evaporative cooling. But the key innovation was in how they handled the atoms after creating the Bose-Einstein condensate. At such low temperatures, atoms can't be kept in physical containers because they would stick to the walls and warm up. Instead, they had to be suspended using magnetic fields, creating a magnetic trap. The team carefully controlled the shape and strength of this trap, slowly expanding it to allow the BEC to spread out. This further reduced the density and, through clever manipulation of the magnetic fields, reduced the effective temperature to an unprecedented level. But even this record was eventually broken. In 2021, researchers in Germany achieved an effective temperature of just 38 picokelvin using Bose-Einstein condensates in free fall. They used the drop tower at the Center of Applied Space Technology and Microgravity in Bremen, Germany, a facility that allows experiments in near weightlessness for several seconds. By using matter wave lensing, a technique that manipulates the quantum wave properties of atoms. They were able to control the expansion of the BX during free fall and achieve this record low effective temperature. This temperature is so close to absolute zero that it's difficult to comprehend. At 38 picokelvin, the atoms have almost no thermal energy at all. They exist in a realm where quantum mechanics completely dominates, and classical physics has no relevance whatsoever. More recently, in 2024, researchers at Columbia University achieved another milestone. They created the first Bose-Einstein condensate made from molecules rather than individual atoms. Using sodium-cesium molecules, they cooled them to about 5 nanokelvin and maintained the condensate for about 2 seconds, an unusually long time for such experiments. This achievement opens new possibilities for studying quantum phenomena and developing quantum technologies, because molecules have more complex internal structure than atoms and can interact in more varied ways. Why do scientists work so hard to reach these extreme cold temperatures? Beyond the pure scientific curiosity of exploring the limits of what's possible, ultra-cold atoms have practical applications. They can be used to build incredibly precise atomic clocks, far more accurate than any previous timekeeping device. These clocks are essential for GPS systems, telecommunications networks, and fundamental physics experiments. Ultra-cold atoms can also be used as sensors for gravity and rotation, with applications in navigation, geology, and fundamental tests of general relativity. They're used in quantum simulations, where physicists use one quantum system to study another quantum system that might be too complex to analyze directly. And they're at the heart of efforts to build quantum computers, devices that could revolutionize computing by exploiting quantum mechanical effects. The quest for absolute zero continues. While we can never reach it exactly, each step closer reveals new physics, new phenomena, new possibilities. The temperatures achieved in these laboratories represent the coldest matter that has existed in the universe since the very early moments after the Big Bang. For those first fractions of a second, the entire universe was extraordinarily hot. But as it expanded and cooled, matter formed and temperatures dropped. Today, the background temperature of the universe is about 2.7 Kelvin. Human laboratories have created matter more than 1 billion times colder than this cosmic average. We've created the coldest places in the universe, tiny pockets of near-perfect stillness in a cosmos filled with motion and energy. Now let's talk about that background temperature of the universe itself. When you look up at the night sky, what you're really looking at is mostly empty space. Between the stars, between the galaxies, there's a vast expanse of near-perfect vacuum. But this vacuum isn't truly empty, and it's not at absolute zero. All of space is filled with a faint glow of microwave radiation, invisible to our eyes, but detectable with specialized instruments. This radiation is the cosmic microwave background, or CMB, and it has a temperature of approximately 2.725 Kelvin. The cosmic microwave background is the remnant heat from the Big Bang itself. In the very early universe, about 13.8 billion years ago, all of space was filled with an extremely hot, dense plasma. Photons, electrons, protons, and other particles were all mixed together in a seething soup. The temperature was so high that atoms couldn't form. Anytime a proton and electron tried to combine into a hydrogen atom, a high-energy photon would immediately blast them apart again. The universe was opaque to light because photons couldn't travel far before interacting with this plasma. As the universe expanded, it cooled. About 380,000 years after the Big Bang, the temperature dropped below about 3,000 Kelvin. At this temperature, protons and electrons could finally combine to form neutral hydrogen atoms, and they stayed combined. This event is called recombination. When recombination occurred, the universe suddenly became transparent. Photons that had been constantly scattering off charged particles could now travel freely through space. The universe was filled with this thermal radiation, and it's been traveling through space ever since. But the universe has continued to expand since recombination. As space expands, the wavelengths of these photons get stretched out, a phenomenon called cosmological redshift. Radiation that started out as visible or infrared light, corresponding to a temperature of 3,000 Kelvin, has been stretched to microwave wavelengths, corresponding to a temperature of about 2.7 Kelvin. This is what we observe as the cosmic microwave background. It's a perfect snapshot of the universe as it was 380,000 years after the Big Bang, and it tells us that every cubic centimeter of space today is bathed in radiation with a temperature of 2.725 Kelvin. This might seem cold, and it is certainly colder than anything we experience on Earth's surface, but it's nowhere near absolute zero. If you could somehow place a thermometer in the depths of intergalactic space, far from any stars or galaxies, it would eventually equilibrate with this background radiation and settle at 2.725 Kelvin. This is the baseline temperature of the universe. Any object in space, if it's not generating its own heat or receiving heat from nearby sources, will cool until it reaches this temperature. It represents a kind of cosmic floor, the minimum temperature of empty space. The cosmic microwave background is remarkably uniform. No matter which direction you look in space, the temperature is the same to within about 1 part in 100,000. There are tiny fluctuations, regions that are slightly hotter or colder than the average, but these variations are incredibly small. These fluctuations are actually crucial to our understanding of how the universe evolved. They represent tiny density variations in the early universe, regions where matter was slightly more or less concentrated. Over billions of years, gravity amplified these variations, causing denser regions to collapse and form galaxies, stars, and eventually planets and people. Studying the cosmic microwave background has been one of the great triumphs of modern cosmology. Satellites like the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck satellite have mapped the CMB with exquisite precision. From these maps, cosmologists have been able to determine fundamental properties of the universe with remarkable accuracy. We know the age of the universe is 13.8 billion years. We know the universe is spatially flat, neither curved inward like a sphere, nor outward like a saddle. We know the composition of the universe, that ordinary matter makes up only about 5%, with dark matter comprising about 27%, and dark energy about 68%. All of this information comes from carefully analyzing the temperature variations in the cosmic microwave background. The CMB temperature is slowly decreasing as the universe expands. In another 13.8 billion years, when the universe is twice its current age, the temperature will have dropped to about 1.4 Kelvin. In the far future, trillions of years from now, the temperature will approach absolute zero asymptotically, though it will never quite reach it. The universe is cooling, and this cooling is fundamentally tied to its expansion. In a sense, the entire universe is undergoing adiabatic expansion, just like the gas in the Boomerang Nebula, though at a much slower rate. This background temperature sets a limit on how cold objects in space can naturally become, unless something is actively cooling, like the rapid expansion of gas in the Boomerang Nebula. It can't get colder than 2.7 Kelvin just by sitting in space. This makes the achievement of laboratories on Earth even more remarkable. We've created environments colder than the coldest depths of space, colder than anywhere in the natural universe. Now let's shift our perspective dramatically. Let's move from the coldest extremes to the realm of everyday stellar temperatures. Let's talk about our sun. The sun is a fairly ordinary star, a middle-aged, medium-sized ball of plasma about 1.4 million kilometers in diameter. It's been shining steadily for about 4.6 billion years and will continue for roughly another 5 billion years before it exhausts its hydrogen fuel and begins to die. The sun's energy comes from nuclear fusion reactions in its core, where hydrogen nuclei fuse together to form helium, releasing tremendous amounts of energy in the process. But what's the temperature of the sun? The answer depends on where you're measuring. The sun isn't a uniform object. It has distinct layers, each with its own temperature. The visible surface of the sun, the part we see when we look at it, is called the photosphere. This is where most of the sun's light is emitted. The temperature of the photosphere is about 5,700 Kelvin, sometimes cited as 5,800 Kelvin, or approximately 5,400 degrees Celsius. This temperature gives the sun its characteristic yellow-white color. Hotter stars glow blue or white. Cooler stars glow orange or red. Above the photosphere is the sun's atmosphere, which has two main layers. The chromosphere, a thin layer just above the photosphere, has a temperature of about 4,000 to 20,000 Kelvin. Above that is the corona, the sun's outer atmosphere, which extends millions of kilometers into space. Surprisingly, the corona is much hotter than the surface, with temperatures reaching 1 to 3 million Kelvin. This seems to violate thermodynamics. How can the outer layer be hotter than the inner layer? The answer is that the corona isn't heated by thermal conduction from below. Instead, it's heated by magnetic fields that extend from the sun's interior into the atmosphere. These fields store energy and release it through processes we don't fully understand, heating the corona to these extreme temperatures. But the real action happens deep in the sun's core. At the very center of the sun, the temperature reaches about 15 million Kelvin. That's 15 million degrees Celsius, or about 27 million degrees Fahrenheit. At these temperatures, hydrogen nuclei are moving fast enough that when they collide, they can overcome the electromagnetic repulsion between positively charged protons and get close enough for the strong nuclear force to take over. When 4 hydrogen nuclei fuse together to form one helium nucleus, a small amount of mass is converted to energy according to Einstein's famous equation, E equals mc squared. This energy works its way out through the sun over hundreds of thousands of years, eventually emerging as the sunlight that warms Earth. The sun converts about 600 million tons of hydrogen into helium every second. Of this, about 4 million tons of mass is converted directly into energy. This sounds like a lot, but the sun is so massive that it can sustain this rate for billions of years. Over its 10 billion year main sequence lifetime, the sun will convert about 100 times the mass of Earth into energy. That's only about 0.03% of its total mass, but it's enough to keep the sun shining steadily throughout the entire history of complex life on Earth. Astronomers classify stars based on their surface temperature using a system called spectral classification. The main classes, from hottest to coolest, are O, B, A, F, G, K, and M. Astronomy students remember this sequence with mnemonics like "Oh, be a fine girl, kiss me." Each class is further subdivided from 0 to 9, with 0 being the hottest and 9 the coolest within that class. Our sun is classified as a G2 star. This means it's a G-type star with a surface temperature slightly hotter than the average G-type star. G-type stars have surface temperatures between 5,200 and 6,000 Kelvin and appear yellow. Other familiar stars span the range of spectral types. Betelgeuse, the red supergiant in the constellation Orion, is an M-type star with a surface temperature of only about 3,500 Kelvin. It appears distinctly red even to the naked eye. Sirius, the brightest star in the night sky, is an A-type star with a surface temperature of about 9,900 Kelvin. It appears brilliant white with a slight blue tinge. Rigel, another bright star in Orion, is a B-type star with a surface temperature around 12,000 Kelvin, giving it a blue-white color. These surface temperatures tell us a lot about a star's properties. Hotter stars are generally more massive and more luminous. They burn through their fuel faster and have shorter lifetimes. The hottest O-type stars might only live a few million years before exploding as supernovae. The coolest M-type stars can live for trillions of years, far longer than the current age of the universe. Every red dwarf that has ever formed is still shining today. The sun, as a middle-of-the-range G-type star, has a lifetime of about 10 billion years, and it's currently about halfway through its main sequence phase. The temperature of a star's core is always much higher than its surface temperature because fusion requires extreme temperatures. For a star like the sun, the core temperature is about 15 million Kelvin. More massive stars have even hotter cores. A star 20 times more massive than the sun might have a core temperature of 50 million Kelvin or more. These extreme core temperatures allow more massive stars to fuse not just hydrogen into helium, but helium into carbon and oxygen, and in the most massive stars, carbon into heavier elements, all the way up to iron. The sun represents a comfortable middle ground in the temperature spectrum of stars. It's hot enough to sustain fusion and shine for billions of years, but not so hot that it burns out quickly. Its surface temperature of 5,700 Kelvin is warm enough to provide life-giving light and heat to Earth, but not so hot that it would sterilize nearby planets with intense radiation. We exist in a temperature sweet spot, orbiting a star of moderate temperature, living on a planet with surface temperatures that allow liquid water to exist. This narrow temperature range is essential for life as we know it. But what about the hottest stars in the universe? While our sun is respectably hot, it's far from the extreme. There are stars with surface temperatures 10 times hotter than the sun, and core temperatures that dwarf even the most massive main sequence stars. The hottest stars in the universe are the massive O-type stars, and an even more extreme class called Wolf-Rayet stars. These stellar furnaces push the limits of how hot a stable star can be, reaching temperatures that allow us to glimpse the conditions of the early universe. O-type stars are the rarest and most extreme of the main sequence stars. They have masses ranging from about 16 to 100 times the mass of the Sun. Their surface temperatures range from about 30,000 Kelvin up to over 60,000 Kelvin for the hottest examples. At these temperatures, stars emit most of their light in the ultraviolet part of the spectrum, invisible to our eyes. What little visible light they do emit appears blue-white. These stars are incredibly luminous, outshining the Sun by factors of hundreds of thousands or even millions. A single O-type star can emit as much light as an entire small galaxy. In the core of an O-type star, temperatures reach extraordinary levels. The most massive O stars have core temperatures exceeding 100 million Kelvin. At these temperatures, not only does hydrogen fuse into helium, but helium begins fusing into carbon and oxygen even while the star is still on the main sequence. These stars burn through their fuel at a prodigious rate. A star 100 times the mass of the Sun might last only a few million years before exhausting its hydrogen. That's less than 1,000th the lifetime of the Sun. Because O-type stars are so rare and short-lived, and because they emit most of their light in the ultraviolet, we don't have many familiar examples. One of the best-known O-type stars is Zeta Puppis, also called Naos. It has a surface temperature of about 42,000 Kelvin and is one of the brightest stars in the night sky, though much of its light is in the ultraviolet and therefore invisible to us. Another example is Lambda Orionis, the head of Orion, with a surface temperature around 37,000 Kelvin. Even hotter than O-type stars are the Wolf-Rayet stars, named after French astronomers Charles Wolf and Georges Rayet, who first identified them in 1867. These are the exposed cores of extremely massive stars that have shed their outer hydrogen envelopes. What we see is the bare helium and carbon-rich core, burning at extreme temperatures. Wolf-Rayet stars have surface temperatures ranging from about 30,000 Kelvin up to an astonishing 200,000 Kelvin for the hottest examples. At these temperatures, the star's peak emission is in the far ultraviolet or even soft X-ray part of the spectrum. These stars are losing mass at enormous rates through powerful stellar winds. A typical Wolf-Rayet star might lose the equivalent of Earth's mass every 10,000 years. These winds, driven by intense radiation pressure, create expanding shells of gas around the star that glow brightly in emission lines. This makes Wolf-Rayet stars easy to identify spectroscopically, despite being relatively rare. Only a few hundred Wolf-Rayet stars are known in our galaxy. Wolf-Rayet stars are incredibly short-lived. They represent a late stage of evolution for the most massive stars. After spending a few million years as an O-type star, a very massive star will swell into a supergiant, developing fierce stellar winds that strip away its outer layers. What remains is the Wolf-Rayet star, a compact, intensely hot core that will soon explode as a supernova. The total time a star spends in the Wolf-Rayet phase might only be a few 100,000 years. Then the core collapses and the star ends its life in one of the most energetic events in the universe. But even Wolf-Rayet stars, hot as they are, don't represent the highest temperatures found in stars. To find truly extreme stellar temperatures, we need to look at the remnants of dead stars. Specifically, we need to look at white dwarfs, particularly the youngest, hottest white dwarfs that have just been exposed after a star sheds its outer layers. The central star of a planetary nebula can have a surface temperature exceeding 100,000 Kelvin, and in rare cases, reaching temperatures over 500,000 Kelvin. The hottest known stellar surface belongs to the central star of the Red Spider Nebula, officially designated NGC 6202. Observations indicate this star has a surface temperature estimated at approximately 500,000 Kelvin or higher. Some measurements suggest it could reach as high as 540,000 Kelvin. That's more than 90 times hotter than the Sun's surface and about 30 times hotter than Sirius, one of the hottest stars visible to the naked eye. At this temperature, the star emits almost all of its energy as ultraviolet and X-ray radiation. The visible light it produces is minimal. Yet this tiny star, probably no larger than Earth, is incredibly luminous because of its extreme temperature. It illuminates the surrounding planetary nebula with intense ultraviolet radiation, causing the gas to fluoresce in brilliant reds and blues. How can a white dwarf be so hot? White dwarfs are the remnants of stars, like the Sun, after they've exhausted their nuclear fuel. When the Sun runs out of hydrogen, it will swell into a red giant, then shed its outer layers, exposing its hot core. This core, with no more fusion reactions to support it, will contract under its own gravity until electron degeneracy pressure, a quantum mechanical effect, halts the collapse. The result is a white dwarf, an object about the size of Earth, but with a mass similar to the Sun. When first exposed, the surface of this white dwarf is incredibly hot, heated by the residual energy from the star's previous fusion reactions and from the gravitational energy released during the collapse. A newly formed white dwarf might have a surface temperature of 100,000 Kelvin or more, but with no internal heat source, it begins to cool. Over millions of years, the white dwarf radiates its heat into space, gradually dimming and cooling. After about 10 billion years, a white dwarf will cool to a few thousand Kelvin, becoming a black dwarf. Though the universe isn't old enough yet for any black dwarfs to exist, the hottest white dwarfs we observe are those that have just recently been exposed, still glowing with the heat of their formation. These extremely hot white dwarfs represent some of the highest surface temperatures found in stable stellar objects, but they're not the hottest temperatures in the universe. For that, we need to look at more violent, transient events. We need to look at supernovae and their remnants. We need to look at the moment when a massive star dies and its core collapses into a neutron star. During this cataclysmic event, temperatures reach levels that rival the early universe itself. When a massive star, one with an initial mass more than about 8 times the mass of the Sun, exhausts all its nuclear fuel, catastrophe strikes. Over its lifetime, the star has fused hydrogen into helium, helium into carbon and oxygen, carbon into neon and magnesium, neon into oxygen and magnesium, oxygen into silicon and sulfur, and finally silicon into iron. This process creates a structure like an onion with shells of different elements surrounding an iron core. But iron is special. It's the most stable nucleus. Fusing iron into heavier elements doesn't release energy. Instead, it requires energy. When the iron core grows too large, there's no more fusion to generate outward pressure to balance gravity. The core collapses. This collapse happens incredibly fast. In less than a second, the core, roughly the size of Earth, collapses to a sphere about 20 kilometers in diameter. The density becomes so extreme that it approaches the density of an atomic nucleus. Electrons are crushed into protons, forming neutrons and releasing a flood of neutrinos. Models suggest the temperature during this phase skyrockets to approximately 100 billion Kelvin. That's 100,000 million Kelvin, or 100,000 times hotter than the core of the Sun. At this temperature, the kinetic energy of particles is so high that nuclei begin to break apart, a process called photodisintegration. The iron nuclei that the star worked so hard to create disintegrate back into helium nuclei and individual protons and neutrons. When the collapse finally halts, stopped by neutron degeneracy pressure and the repulsive force between neutrons in contact, the infalling material rebounds. This creates a shock wave that propagates outward through the star. The energy from this shock, combined with energy absorbed from the neutrinos flooding out of the newly formed neutron star core, blasts the star's outer layers into space at speeds of tens of thousands of kilometers per second. This is a supernova explosion. The explosion releases about 10 to the power of 44 joules of energy in the form of kinetic energy and light. That's roughly 100 times the energy the Sun will emit over its entire 10 billion year lifetime, released in a matter of days. The newly formed neutron star at the center has an initial temperature of about 100 billion Kelvin. This is the hottest stable matter in the modern universe. Matter heated to temperatures that haven't existed naturally since the first moments after the Big Bang. At these temperatures, the distinction between different types of particles begins to blur. Neutrinos are created in vast numbers through various processes. The core is so hot and dense that even neutrinos, which barely interact with matter under normal conditions, are trapped for several seconds before escaping. When they do escape, they carry away most of the energy from the supernova, about 10 to the power of 46 joules. This neutrino burst lasts about 10 seconds, releasing energy at a rate greater than all the light from all the stars in the observable universe combined. The neutron star doesn't stay at 100 billion Kelvin for long. With no fusion to generate new heat, it begins to cool rapidly through neutrino emission. Within a few minutes, the core temperature drops to about 10 billion Kelvin. Within a few years, it cools to about 1,000,000 Kelvin. After that, cooling continues more slowly through photon emission from the surface. A million-year-old neutron star might have a surface temperature of about 1,000,000 Kelvin. Ancient neutron stars, billions of years old, might cool to a few thousand Kelvin, still hot by everyday standards, but cool compared to their birth temperatures. These temperatures from supernova explosions represent the highest temperatures found in discrete astronomical objects in the modern universe, but they're still far from the ultimate temperature extremes. To go higher, we need to leave the realm of natural astrophysical phenomena and enter the world of high-energy physics experiments. We need to look at what happens when scientists use particle accelerators to smash heavy atomic nuclei together at nearly the speed of light. These collisions create, for the briefest instant, the hottest matter ever produced on Earth, and the hottest matter in the universe since the Big Bang itself. The story of these ultra-hot experiments begins with a simple question: what was the universe like in the first moments after the Big Bang? We know that as we look back in time, the universe becomes hotter and denser. At 380,000 years after the Big Bang, it was hot enough that atoms couldn't exist. Earlier still, at about 3 minutes after the Big Bang, it was hot enough that atomic nuclei couldn't exist. Only protons and neutrons were stable. Going back even further to about 1 microsecond after the Big Bang, the temperature was so high that even protons and neutrons couldn't exist. At temperatures above about 170 megaelectron-volts, which corresponds to about 2 trillion Kelvin, protons and neutrons melt into their constituent quarks and gluons. The universe was filled with a soup of free quarks, gluons, and other particles. This state of matter is called a quark-gluon plasma, or QGP. Quarks are the fundamental building blocks of protons and neutrons. Each proton consists of 2 up quarks and 1 down quark. Each neutron consists of 1 up quark and 2 down quarks. The quarks are held together by particles called gluons, which mediate the strong nuclear force. Under normal conditions, quarks are never found in isolation. They're always confined inside protons, neutrons, or other composite particles called hadrons. This is called confinement, and it's a fundamental property of the strong force. But at sufficiently high temperatures, confinement breaks down. Quarks and gluons become free to roam independently, forming a quark. Gluon plasma. To recreate this primordial state of matter, physicists needed to create extremely high temperatures and densities. The way to do this is to collide heavy atomic nuclei at relativistic speeds. When 2 large nuclei collide head-on, all their kinetic energy is dumped into a tiny volume for a tiny instant. If the collision energy is high enough, the result is a fireball of quark-gluon plasma, a momentary recreation of conditions from the first microsecond of the universe. The first facility capable of creating quark-gluon plasma was the Relativistic Heavy Ion Collider, or RHIC, at Brookhaven National Laboratory in New York. RHIC is a circular accelerator about 3.8 kilometers in circumference. It accelerates 2 beams of heavy ions, typically gold nuclei in opposite directions, to nearly the speed of light, then smashes them together. The first collisions occurred in the year 2000. By carefully studying the debris from billions of collisions, physicists confirmed that they had created quark-gluon plasma. The temperature in these collisions was estimated at about 4 trillion Kelvin, or 4 million Kelvin. That's more than 250,000 times hotter than the core of the Sun, and comparable to the temperature of the universe when it was about 1 microsecond old. But RHIC wasn't the only facility pursuing quark-gluon plasma. In 2008, the Large Hadron Collider, or LHC, at CERN near Geneva, Switzerland, came online. The LHC is much larger than RHIC, with a circumference of 27 kilometers, and it can accelerate particles to higher energies. While the LHC's primary purpose is to collide protons to study fundamental particles like the Higgs boson, it also collides heavy ions, specifically lead nuclei. In 2010, the LHC began its heavy ion program. The first lead ion collisions at the LHC reached energies far higher than RHIC could achieve. In August 2012, the ALICE experiment, one of the large detectors at the LHC specifically designed to study quark-gluon plasma, announced achieving a record temperature. Analysis of these collisions indicated the quark-gluon plasma reached approximately 5.5 trillion Kelvin. This represents the highest temperature confirmed to be created in controlled laboratory conditions on Earth. To put this temperature in perspective, 5.5 trillion Kelvin corresponds to an energy scale of about 500 megaelectron volts per particle. At this temperature, not only are protons and neutrons melted into quarks and gluons, but the plasma exhibits exotic behaviors that don't exist anywhere else in the universe today. The quark-gluon plasma created in these collisions doesn't behave like a gas, as physicists initially expected. Instead, it behaves like a nearly perfect fluid with almost no viscosity. This means it flows with minimal friction, somewhat like a superfluid. This unexpected property has forced physicists to revise their understanding of how matter behaves at these extreme temperatures. The quark-gluon plasma only exists for an incredibly brief time. In the LHC collisions, the plasma forms exists for about 10 to the power of minus 23 seconds. That's less than a trillionth of a second, and then cools and expands. As it cools, the quarks recombine into hadrons, creating a spray of particles that fly outward in all directions. Detectors surrounding the collision point measure these particles, analyzing their energies, momenta, and types to reconstruct what happened during those fleeting moments when quark-gluon plasma existed. Creating quark-gluon plasma in the laboratory is an extraordinary achievement. We're recreating conditions that last occurred naturally in the universe, about 1 microsecond after the Big Bang. Since then, nowhere in the universe has matter been this hot, except possibly in the cores of neutron stars. Immediately after they form, though that's still debated, these experiments push temperature to extremes that allow us to test our theories of the strong force and of how the universe evolved in its earliest moments. But even 5.5 trillion Kelvin isn't the highest temperature physics allows. There are theoretical limits to temperature, just as there are limits to cold. Just as absolute zero represents the coldest possible temperature, there's a theoretical maximum temperature, a point where our current understanding of physics breaks down. This temperature is called the Planck temperature, and it's so extreme that it may have only existed in the first instant after the Big Bang, if it existed at all. The Planck temperature is derived from fundamental constants of nature. Specifically, it's calculated using the gravitational constant, the speed of light, Planck's constant, and the Boltzmann constant. When you combine these in the right way, you get a temperature of approximately 1.417 times 10 to the power of 32 Kelvin. That's about 142 nonillion Kelvin. To write it out, that's 142 million trillion Kelvin. This is the Planck temperature. What does the Planck temperature represent? At this temperature, the wavelength of thermal radiation becomes comparable to the Planck length, which is about 10 to the power of minus 35 meters. The Planck length is thought to be the smallest meaningful length in physics. Below this scale, quantum effects of gravity become important, and our current theories, which separate quantum mechanics from general relativity, break down. We would need a theory of quantum gravity to describe what happens at the Planck scale, and we don't have such a theory yet. At the Planck temperature, the gravitational force becomes as strong as the other fundamental forces. Normally, gravity is by far the weakest force. The electromagnetic force holding an electron to a proton is about 10 to the power of 40 times stronger than the gravitational force between them. But at the Planck temperature, gravity catches up. At these energies, all four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, would have comparable strengths. Physicists believe these forces might unify into a single force at these temperatures. Another way to think about the Planck temperature is in terms of energy. Temperature is really just a measure of energy per particle. The Planck temperature corresponds to an energy of about 10 to the power of 19 giga-electron volts per particle. At these energies, any particle would be so energetic that its mass energy would be compressed into a volume smaller than the Planck length. According to our understanding of physics, this would create a micro black hole. In effect, adding more energy to make something hotter would just create black holes, which would then evaporate through Hawking radiation. This suggests that the Planck temperature might be a practical upper limit to temperature, though the theoretical situation is unclear. Did the universe ever reach the Planck temperature? Standard Big Bang cosmology suggests it may have approached this temperature, but only in the very first instant. The earliest time we can meaningfully discuss using current physics is the Planck time, about 10 to the power of minus 43 seconds after the Big Bang. Based on theoretical models, at this moment, the temperature would have been on the order of the Planck temperature. Before this time, our current theories break down completely. We need a theory of quantum gravity, something like string theory or loop quantum gravity, to understand the universe at times earlier than the Planck time. As the universe expanded and cooled from this initial state, the temperature dropped rapidly. By 10 to the power of minus 35 seconds, the temperature had fallen to about 10 to the power of 28 Kelvin. By 10 to the power of minus 6 seconds, 1 microsecond, the temperature was down to about 10 to the power of 13 Kelvin, or 10 trillion Kelvin. This is roughly the temperature recreated in heavy ion collisions at the LHC. By 3 minutes, the temperature was down to about 1 billion Kelvin, cool enough for protons and neutrons to combine into light nuclei. By 380,000 years, the temperature was about 3,000 Kelvin, cool enough for atoms to form. Today, 13.8 billion years later, the temperature of the cosmic microwave background is about 2.7 Kelvin. The history of the universe is a story of cooling. From the unimaginable heat of the Planck temperature to the frigid near vacuum of intergalactic space today, temperature has dropped by more than 30 orders of magnitude. This cooling allowed structure to form. Hot particles move too fast to be bound by gravity. As the universe cooled, particles slowed down enough that gravity could pull them together into atoms, then molecules, then dust grains, then asteroids and planets, then stars, then galaxies. All the complexity and beauty of the universe emerged from this cosmic cooling. Will the universe continue to cool forever? According to our current understanding, yes. The universe is expanding, and current observations suggest this expansion is accelerating due to dark energy. As space expands, the cosmic microwave background will continue to redshift to longer wavelengths, corresponding to lower temperatures. In about 100 billion years, the CMB temperature will drop below 1 Kelvin. In about a trillion years, it will approach 0.01 Kelvin. The universe will continue cooling toward absolute zero, though it will never quite reach it. Stars will burn out. Black holes will evaporate through Hawking radiation. In the unimaginably distant future, tens of Google years from now, the universe will be cold, dark, and empty, with a temperature infinitesimally close to absolute zero. But let's return to the present and consider what these temperature extremes mean for existence. Temperature isn't just an abstract number. It determines the state of matter, the chemical reactions that are possible, and ultimately, whether life can exist. We exist in a remarkably narrow temperature range. The surface of Earth ranges from about 230 Kelvin in the coldest places to about 320 Kelvin in the hottest deserts. That's a range of about 90 Kelvin. Liquid water, essential for life as we know it, exists between 273 and 373 Kelvin at normal atmospheric pressure. Human body temperature is about 310 Kelvin. A deviation of just a few degrees above or below this can be fatal. At temperatures below about 250 Kelvin, most biochemical processes slow to a crawl or stop entirely. At temperatures above about 350 Kelvin, proteins begin to denature and lose their function. Complex life requires a narrow temperature window, and Earth happens to be in that window, neither too hot nor too cold. This is partly due to our distance from the sun, partly due to our atmosphere, which traps heat through the greenhouse effect, and partly due to luck. At the extremes we've discussed, life is impossible. At temperatures near absolute zero, all chemical reactions stop. Molecules lack the energy to interact. There's no metabolism, no growth, no reproduction. At temperatures in the thousands of Kelvin, molecules break apart. Above about 10,000 Kelvin, even atoms ionize, losing their electrons. Above 1,000,000 Kelvin, atomic nuclei begin to break apart through photodisintegration. Above 1,000,000,000 Kelvin, even atomic nuclei can't exist. Above 1,000,000,000,000 Kelvin, protons and neutrons dissolve into quarks and gluons. And at the Planck temperature, the very structure of space-time breaks down. Life requires not just moderate temperatures, but stable temperatures. The Earth's temperature has remained roughly constant, varying by no more than about 30 Kelvin for billions of years. This stability allowed life to evolve and adapt. If the Earth's temperature had fluctuated wildly, swinging from freezing to boiling and back, life might never have emerged. The sun's steady output, the Earth's orbit, our atmosphere, and even the moon's stabilizing effect on Earth's rotation all contribute to this temperature stability. Thinking about temperature extremes also reveals how unusual our environment is. We live on the surface of a planet orbiting a star. The planet has a temperature of around 300 Kelvin. The star's surface is about 5,700 Kelvin. Between the planet and the star is mostly empty space at about 2.7 Kelvin. Below our feet, the Earth's interior reaches about 7,000 Kelvin at the core, hotter than the sun's surface. Above our heads, in the sun's corona, temperatures reach millions of Kelvin. We exist in a narrow shell, a thin layer where conditions happen to be right for liquid water and complex chemistry. Looking beyond Earth, most of the universe is hostile to life as we know it. The interiors of stars are too hot. The depths of space are too cold. Only on the surfaces of planets and moons, in a narrow range of distances from their stars, can temperatures be moderate enough for life? Even then, most planets are either too hot or too cold. Venus, closer to the Sun, has a surface temperature of about 730 Kelvin, hot enough to melt lead. Mars, farther from the Sun, has an average temperature of about 210 Kelvin, well below the freezing point of water. Earth, in the middle, is just right, at least for now. The temperature extremes we've explored span an almost incomprehensible range. From 38 picokelvin in a laboratory in Germany, just barely above absolute zero, to 5.5 trillion Kelvin in a particle collision at CERN, and theoretically up to the Planck temperature of 10 to the power of 32 Kelvin. The range covers more than 40 orders of magnitude. That's a factor of 10,000 trillion. The coldest and hottest temperatures differ by a ratio far greater than the ratio between the size of an atom and the size of the observable universe. Humans have achieved something remarkable. We've created the coldest matter in the universe and the hottest matter in the universe, both within laboratories here on Earth. We've pushed to within a trillionth of a degree of absolute zero, and we've recreated temperatures that last existed in the first microsecond after the Big Bang. These achievements required centuries of scientific progress, building on the work of thousands of researchers, developing new theories, new technologies, new techniques. From the early understanding of heat and temperature in the 18th century, to the development of thermodynamics in the 19th century, to quantum mechanics in the 20th century, to the ultra-cold atom experiments and heavy ion collisions of the 21st century, each advance brought us closer to understanding and controlling the temperature extremes of our universe. These experiments aren't just curiosities. They have practical applications, and they advance our fundamental understanding of physics. Ultra-cold atoms are used in the most precise atomic clocks ever built, clocks accurate to within 1 second over billions of years. These clocks are essential for GPS navigation, telecommunications, and fundamental physics experiments. They're also used in quantum sensors that can detect incredibly tiny variations in gravity or rotation, with applications in mineral exploration, earthquake prediction, and even detecting gravitational waves. Quark-gluon plasma experiments help us understand the strong force, one of the 4 fundamental forces of nature. They allow us to test predictions of quantum chromodynamics, the theory that describes how quarks and gluons interact. They help us understand how matter behaves at extreme densities and temperatures, which is relevant for understanding neutron stars and the early universe. And they push the boundaries of what's possible with particle accelerators, developing technologies that have spin-offs in medicine, materials science, and computing. Beyond the practical applications, these experiments address deep questions about the nature of reality. What is the coldest possible temperature? Can we ever reach absolute zero? What is the hottest possible temperature? What happened in the first moments after the Big Bang? How did the universe evolve from a hot, dense plasma to the complex structure we see today? What are the fundamental limits of physics? By exploring temperature extremes, we're exploring the limits of what's possible in our universe. As we look to the future, research at temperature extremes continues. New ultra-cold atom experiments are planned for the International Space Station, where microgravity will allow even colder temperatures and longer observation times. The Cold Atom Laboratory on the ISS is already producing Bose-Einstein condensates in space, achieving effective temperatures in the picokelvin range. Future experiments might reach even colder temperatures, perhaps approaching a billionth of a degree above absolute zero. On the hot side, future particle accelerators might reach even higher energies and temperatures. The proposed future circular collider at CERN would be 100 kilometers in circumference, nearly 4 times larger than the current LHC, and could achieve collision energies 10 times higher. This might create quark-gluon plasma at temperatures exceeding 50 trillion Kelvin, pushing even closer to the conditions of the earliest moments of the Big Bang. These experiments could reveal new physics, new particles, new forces, new insights into how the universe works. Standing back and considering the full temperature spectrum, from the coldest cold to the hottest hot, reveals something profound about our universe. It's a universe of extremes, a universe where temperatures span an enormous range, where matter can exist in states from near perfect stillness to violent chaos. And yet, somewhere in the middle of this range, there's a narrow band where conditions are gentle enough for complexity to emerge, a band where atoms can combine into molecules, molecules into cells, cells into organisms, organisms into beings, capable of wonder and curiosity, a band where life, intelligence, and consciousness can exist. We exist because the temperature of our environment falls within this narrow band. We evolved on a planet whose surface temperature allowed liquid water to exist. We orbit a star whose core temperature is high enough to fuse hydrogen, but not so high that it burns out quickly. We emerged at a time when the universe had cooled from its initial fireball to a temperature that allowed galaxies, stars, and planets to form. The temperature of our environment, seemingly so ordinary, is actually extraordinarily special. Every breath you take, every heartbeat, every thought you think depends on temperatures being within a narrow range. Too cold, and the chemical reactions of life stop. Too hot, and the molecules of life break apart. We exist in a Goldilocks zone, not just in terms of our distance from the sun, but in terms of the temperature of our environment. And this isn't just true for humans. All life on Earth exists in this same narrow range. Even extremophile bacteria that live in boiling hot springs or in Antarctic ice exist at temperatures far from absolute zero and far from the temperatures of stellar cores. The universe as a whole is cooling, slowly but inexorably, as it expands. The early universe was unimaginably hot, too hot for atoms, too hot for nuclei, too hot even for protons and neutrons. As it cooled, structure emerged. First quarks and gluons combined into protons and neutrons. Then protons and neutrons combined into light atomic nuclei. Then electrons combined with nuclei to form atoms. Then atoms combined into molecules, molecules into dust, dust into planets and stars. All of this was possible because the temperature dropped into the right range. Life is a temporary phenomenon, possible only when temperatures are moderate. In the far future, when all stars have burned out and the universe has cooled to near absolute zero, life will no longer be possible. The brief window when temperatures were right for life will have closed. We exist during a special time in cosmic history, when the universe is neither too young and hot nor too old and cold. We exist in a brief interval, perhaps a few tens of billions of years, out of the entire history of the universe, which might extend for googles of years or even forever. This perspective should fill us with both humility and wonder. Humility because we recognize how small and fragile we are, how dependent on circumstances beyond our control. A slight change in Earth's orbit, a slight variation in the sun's output, and the delicate balance that makes life possible would be disrupted. Wonder because, despite our fragility, despite existing in such a narrow temperature range, we've managed to understand the full spectrum of temperatures in the universe. We've figured out the physics of absolute zero and the Planck temperature. We've created the coldest matter in the universe and the hottest matter since the Big Bang. We've measured the temperature of distant stars and of the cosmic microwave background. We've probed the limits of hot and cold through both observation and experiment. Temperature at its core is about energy and motion. Hot means fast-moving particles with high energy. Cold means slow-moving particles with low energy. But temperature also determines what's possible. It determines the states of matter, the types of interactions, the forms that structure can take. At different temperatures, the universe looks completely different. At the Planck temperature, if it existed, the universe would be a seething foam of quantum fluctuations, with black holes forming and evaporating, with the very fabric of space-time in flux. At temperatures of trillions of Kelvin, matter exists as quark-gluon plasma, a soup of unconfined quarks and gluons. At millions of Kelvin, atoms are fully ionized, existing as plasma. At thousands of Kelvin, molecules break apart, and matter exists as hot gas. At hundreds of Kelvin, we find liquid water and the chemistry of life. At tens of Kelvin, most substances freeze solid. At a few Kelvin, quantum effects become important, and matter can exist as superconductors or superfluids. At microkelvin, Bose-Einstein condensates form. At picokelvin, matter is as cold as we've ever made it, existing in a purely quantum mechanical state. Each of these temperature regimes reveals different physics, different phenomena, different aspects of how the universe works. By exploring the full range of temperatures, we've discovered new states of matter, new principles of physics, new ways that particles and forces interact. We've learned that the universe is far stranger and more varied than everyday experience suggests. We've learned that the comfortable, moderate temperatures we experience are a tiny sliver of what's possible. As we conclude this journey through the temperature extremes of the universe, take a moment to appreciate where you are right now. You're sitting or standing somewhere on Earth's surface at a temperature probably between about 60 and 80 degrees Fahrenheit, or about 15 to 27 degrees Celsius. Around you, air molecules are moving at about 500 meters per second, their kinetic energy corresponding to a temperature of roughly 300 Kelvin. The atoms in your body are vibrating, rotating, moving in ways that maintain your body temperature at precisely 310 Kelvin. This temperature isn't arbitrary. It's the result of billions of years of evolution, fine-tuning our biochemistry to work optimally at this temperature. Above you, the sun shines with a surface temperature of 5,700 Kelvin, its core fusing hydrogen at 15 million Kelvin. Around you, space has a background temperature of 2.7 Kelvin. Below you, Earth's core reaches 7,000 Kelvin. In laboratories around the world, scientists have created matter at 38 picokelvin and at 5.5 trillion Kelvin. In the first instant after the Big Bang, The universe might have reached the Planck temperature of 10 to the power of 32 Kelvin. And throughout all of this, throughout the entire temperature spectrum of the universe, you exist in a narrow, precious range where the temperature is just right for complexity, for life, for thought. The next time you feel hot or cold, remember that you're experiencing a tiny variation within a tiny range of the total temperature spectrum. Remember that the warmth of sunlight on your face represents energy that began as fusion reactions at 15 million Kelvin, traveled through space at 2.7 Kelvin, and warmed your skin to about 310 Kelvin. Remember that the air around you, which feels so ordinary, would be unimaginably hot plasma to someone working at nanokelvin temperatures, and unimaginably cold to someone studying quark gluon plasma. Temperature is relative, but the extremes are absolute. Thank you for joining me on this journey from the coldest cold to the hottest hot, from temperatures near absolute zero to the Planck temperature, from Bose-Einstein condensates to quark gluon plasma, from the Boomerang Nebula to the Large Hadron Collider. If you found this exploration meaningful, please consider liking and subscribing to the channel. Your support helps me continue making these deep dives into the mysteries of science and our place in the universe. Until next time, stay curious about the world around you. Keep wondering about the fundamental properties of nature that make existence possible. Keep marveling at the fact that we, mere collections of atoms at 300 Kelvin, can understand and measure the entire temperature spectrum of the universe, from the coldest matter ever created to the hottest moments after the Big Bang. The universe is full of extremes, but within those extremes, there's a narrow range where wonder and understanding can flourish. We're fortunate to exist in that range, to be able to explore and appreciate the full spectrum of temperatures that make our universe what it is. Sleep well tonight, knowing you share this cosmos with temperature extremes beyond imagination, from the coldest nebula to the hottest plasma, all governed by the same physical laws, all part of the same magnificent universe. Good night.